Here we are at last, part 4, the final installment for the normal maps lecture. Let's talk about a more advanced technique called parallax occlusion mapping. Here we have an example of a really nice normal map. This is using the same technique that we've just outlined. This is a flat plane, perfectly flat geometry, but it has a normal map on it, and that allows it to reflect light differently to give it the illusion that it's got depth. But if you look, you'll see that there's another part of depth that's completely missing from this, and that is something called parallax. It means that when you look at something at an angle like this, you would see things, you'd see the depth in things as raised things block off things behind them. That's thus the name occlusion. A regular normal map gives away the fact that it's fake because it doesn't have any of that effect. This image, on the other hand, shows the more advanced technique. And if we look here, we can see that the raised sections really do look raised up above the flat plane below them. And we can see that the ridges, that this part is sunk down below the ridge and this part is sunk down below this ridge. Really gives it a look of depth. However, this is still being drawn with a single flat plane and using shaders to give it this look. The concept goes a little something like this. Instead of storing the normal of the face, we are going to store the depth of the face. This image here would represent the color. This is the diffuse texture. This is just our regular texture. And this will give us the color of the grays and the browns. This one, we will also have a new texture that represents the depth below the surface. So perhaps the whites, maybe those are high points, and the blacks are deep grooves. So this stone, for example, is raised in this section right here, and then where it meets the joint, it will have a groove that digs down, and then sort of the mortar sort of bulges up again and becomes a little brighter. So that is what we'll store. Now, how do we use it? The idea here is that we're going to do sort of a poor man's ray cast into the depth of the texture to see what pixel we really should hit with our little ray cast. This is a side view, like sort of a side slice, if you will, of across a piece of this texture. Let's say it's crossing across here maybe, and this is the view of what that looks like using this to give us this depth information, right? So the pixels here are showing how tall the three-dimensional image was at this spot, right? So if we take any particular point, let's say we get this high point here, and we sample that in the image. Maybe that's this high point in this diagram. And a lower point, that would be like maybe down here, this is the low point of the diagram. Okay, so that's what this represents. Now, how does this work? The camera is off in this direction. So as we're rendering, as we're rasterizing this triangle, it's rasterizing various pixels along this triangle. One of them is going to be right here. We're going to get UV coordinates at this spot. Maybe that's, right here on the texture map. We know that the way that this was generated was it did a projection back along this ray. So what we can do though is we can say this is, if the surface were flat, if it were flat, this is where that ray would hit, right? So we know that the surface is not flat. So what we'll do is we will look down and look up what is the color of that texture right there. Let me make a little mark. Right here, we're going to go straight down. I'm going to go straight down And right there is the depth at that particular texel. And we can see that this ray looking down from the camera's position towards the surface, if it were flat and high, it would have hit here. But because it's not so high, the ray should really go down deeper. So what we'll do is we'll say, well, imagine that the surface was flat at that height. And we'll come over here. If it were this height, we will project where would that ray actually hit that. And we're going to get right here, this coordinate. So this is our new UV coordinate, right there. We've adjusted it based on the angle that the eye is looking at this surface and the depth that we got before. So we're going to sample from the depth, and we're going to look, and we're going to say, oh, still didn't hit. The depth is still below our projected value. So our new depth, we're going to guess, is about here. So we're going to come over here and say the ray should have hit here. So this is our new UV coordinate. And we say, oh, look, uh-oh, the depth was a little too deep here. Right, a little too deep here. So let's take it back, and we're going to get there. So this is an iterative solution where this is 1, 2, 3, 4 steps of iteration. What we're going to do is we'll sample the depth of the texture at your current UV coordinate, use that depth to calculate what the new UV coordinate should be, and then go over there and take a look. And we'll go around and around and back and forth until we've refined it to however many steps we're going to allow for our particular shader. So by doing that, we can get that really cool depth illusion using our flat surfaces, but there is a limit to how far we can push it. Because this was an iterative solution, we are going to have to limit the number of iterations somewhere. More iterations will allow us to get a better look, and fewer iterations will make us at risk of this artifact, where these ripples are caused by those rays as they go in, and we hit the limit of iteration. Each ray is going to end up in a slightly offset place from where it really ought to belong. And you get a look that, this ripply look like this. So how you'd fix this, there's two ways to fix this. One, just increase the number of iterations if you can afford that. Or the other way is just, if it's not as deep, if the depth that you're cutting into the surface isn't as deep, it won't be as obvious. The parallax occlusion mapping technique gives you a much better illusion of depth than you got from the normal map. But at an extremely increased cost, right? Every time we look up something from a texture map, there's a little bit of a cost to that. And this is going to iteratively look at that depth map multiple times in order to sort out how deep things are. Having said that, we do use this technique in video games. And you might wonder why. Why not just make more geometry to actually give it real depth? The situation here is a trade-off between how many vertices versus how much time is spent in pixel shaders. Remember that as the object moves farther away from the camera, the number of pixels in that object reduces, and that's going to make pixel shaders much less expensive. But as the object moves away, the number of vertices does not necessarily reduce unless we set up some kind of LOD system. So this parallax occlusion mapping is a way we can strike a compromise between how many vertices we're putting in something versus how much time we're spending in the pixel shader. All right, that's it for normal maps. Don't forget to fill out those on Blackboard, that at-home assignment that goes along with all of this, and there will be a lab on this next time. So I'll see you in class.